are slides that come from a Gen Chem 2 run at this in another book. Okay? What was your Gen Chem 2 author? Was it?
Rice University, OpenStax.
Oh, it was OpenStax?
Yeah.
Okay. Well, that may be what this is too. That could be the source of this as well. Oh, I don't want to get in there. Get under there. All right, so here just quickly, efficiencies of some different forms of energy or conversion of energy. Efficiencies, they go all over the map. So the home furnace, methane, burning it 70% efficient. Storage battery, dry cell battery. Electrical to mechanical, so this is electric cars. Electric motor, electric cars, 90% efficiency. So we're going to talk a little bit about efficiencies. The book, Carnot is a French engineer. This is pretty interesting, pretty profound. This predates the first and second law of thermodynamics. So Carnot is looking at steam engines and conversion of doing work with steam engines and trying to figure out how to make steam engines more efficient, what governs the efficiency of a steam engine. And so he digs into this and comes up with something that really kind of leads along. 1824, I don't know, Boltzmann is coming in, 30 years later maybe. But these things are building on one another, and this is kind of fundamental. And if you read chapter 3, you'll see how this flows. So the Carnot engine, and this is right out of the book. And what I want us to do is spend a little bit of time just generally filling in some things here. That's why I gave you this on a full sheet of paper. Okay, so here's the Carnot cycle. And it is every step, there's 4 steps in this, and each step is reversible. So there's an isothermal expansion, step 1, going from A to B. An adiabatic expansion, so you can see volume increasing. Adiabatic expansion, going from B to C. An isothermal compression, going from C to D. And an adiabatic compression, going from D to A. And where do you end up with? You end up where you started. You end up at point A with these state functions. So really nothing's changed from the state function, but the path-dependent functions, heat and work, there are things going on in each one of these steps. So without putting any numbers here, well, we can put some numbers in some cases, but kind of what is going on with heat, work, internal energy, and enthalpy. Now remember, we have these fundamental equations that the change, delta U, change in internal energy, is heat plus work. And delta H is delta U plus delta PV. But so if we have any one of these, pick out any one of these. We got an isothermal expansion. So the temperature is remaining constant. Volume is changing. Temperature is not changing. What's happening with internal energy? the author points out that the partial of internal energy with respect to volume at constant temperature is equal to 0. We won't try to prove or develop that right now, but that's... So what does that tell us? The change in internal energy with a change in volume at constant temperature is 0. So delta U is 0 for an isothermal expansion. Delta U is also going to be 0 for isothermal compression. Okay, now if delta U equals 0, and this is what, and delta U is Q plus W, what does that mean for this isothermal expansion? What can we say about Q and W?
Negative work that's expanding.
Yeah, so
Positive.
so for this one, Q equals negative W for this first step, right? Step 1. So this is negative work. The gas, if we think about an ideal gas in this Carnot cycle, which is where all these things pan out, the system is doing work on the surroundings. The gas is expanding. And heat is going to be positive. It's going to absorb heat. As that gas expands under those conditions, temperature's not changing, but the gas is going to absorb heat from the surroundings. Q equals negative W.
And that's because the only way to keep it at that same temperature would be to absorb heat, right? If you're
Right.
expanding.
Right. Right. Otherwise, it would cool. It would cool down. So yeah, the only way to keep good comment. All right. So it's the way you got to kind of be thinking through some of this. So an adiabatic expansion. Adiabatic, insulated. What does that mean?
Q never change.
Q doesn't change. There's no heat being lost. There's no heat being absorbed. So here Q, this is Q2 equals 0. I should probably label these Q's. So this is Q1. I guess I could make these bigger. Q1 is going to be positive. It's going to have a positive value. It's absorbing energy. Q2 is 0. So what does that tell you about this one here?
They're going to be giving off heat. So it'll be negative Q.
Well, adiabatic compression.
It should be 0 as well because it's adiabatic.
It's going to, compressing it, it seemed like it's going to heat it up, but we're going to do it adiabatically. So Q4 is going to be 0 as well. Isothermal compression. The gas is going to have to give off some heat. This is going to be a negative, and it's going to dissipate the heat to the surroundings. There's going to be a work 2, a work 3, a work 4. We're expanding, we're compressing. So there's expansion, negative adiabatic expansion, negative. These will probably be positive. The surroundings need to compress the gas. Okay, now the delta U of the entire cycle. Remember, delta U overall is the Q of the cycle plus the work of the cycle, the entire cycle. And that's going to be Q1 plus Q3 plus work 1 plus work 2 plus work 3 plus work 4. Okay, so that would be an expression, and this is just kind of developing what is in your book, but I just want to run down through it here pretty quickly. So the Q of the cycle, and some of this is going to disappear because I can't get it all on one slide, is Q1 plus Q3. The heat of the cycle is going to equal the work of the cycle. And that's just flowing out of your delta U equals Q plus W. And since delta U overall is 0, all right, because the cycle, the Carnot cycle starts and ends at the same point, delta U is 0. So the heat of the cycle equals the work of the cycle. All right, and so the first definition of efficiency takes it as a ratio, the negative of the ratio of the work of the cycle divided by the heat from the high temp reservoir. All right, so this Carnot cycle is working between a high temperature reservoir and a low temperature reservoir. It's where the heat is either being, where the surroundings is providing heat to the cycle or the system system is releasing heat to the cold temperature reservoir. So there's these two reservoirs being worked out. So one expression of the efficiency is this. So the heat from the high temperature reservoir is Q1. So one expression of it is the work of the cycle divided by Q1. Okay, now remember, this equals the Q of the cycle, right? That's what we said up here somewhere up there, right here. And what is the Q of the cycle? This equals Q1 plus Q3. So that leads us to this expression. The efficiency equals negative Q1 plus Q3. Wait, I think we can drop this negative sign over Q1. Everybody with me so far? So Q1 over Q1 is 1. So this could be 1 plus Q3 over Q1. And so that's, this is equation 3.6. Okay, I'll just circle that right there. A suggestion I want to make to you as you do your homework, this homework, chapter 3 homework, and even going back into chapter 2 and chapter 1 homework, it wouldn't be a bad idea getting red ink pen or highlighter or something go back and write in the key equation for solving that problem. Where did you get it out of the book? Okay? You're going to be piecing together a piece of paper with some key equations on it to bring into exam 1. So start taking note of where did that come from. Yeah, Graham?
With that, when you get an efficiency over 100%, which is kind of impossible, so I'm just wondering how you like why that equation works. Because if you're doing 1 plus, no matter what your ratio is, unless the ratio is a negative, then you would be having an efficiency over 100%.
This is,
Q3 over 2.
a lot of times this will be negative.
Oh, Q3 itself is negative.
Yeah, Q3 itself is negative.
Okay.
Yeah, you can't get over 100%. As a matter of fact, the second law of thermodynamics is going to basically say it's impossible to even get 100%. Impossible to get 100%. So why is that? Well, let's just go down to, we got to get one more key equation here, and I didn't write down the equation number. But if you carry this on, okay, if you go back to, now if you bring in equation 2.7, 2.7 is basically that work equals negative nRT over the log of the final volume divided by the initial volume. And there's a whole bunch of steps to kind of go through there. But if you go from there and get a ratio of, so I'll just indicate that you got to go through a few steps here to then develop a ratio of Q3 to Q1. You get a big ratio right here where nRT all crosses out, and you can move this over into temperatures instead of the volumes, and you get an expression for the relationship between the Q3 in that Carnot cycle to Q1 in the Carnot cycle that is just simply the ratio of the low temperature reservoir divided by the high temperature reservoir. And so then, well, that equals that. So E, substituting that into this equation up here, okay? Now we're going to just substitute that into that equation, and we get another very important equation for efficiency. I mean, you think of Einstein with E equals mc squared. Here's Carnot with a pretty simple, I mean, basically what it's saying, the efficiency of an engine, any engine, is going to be the theoretical efficiency, best you can do. This is the best you can do for any engine, is going to be the ratio between the low temperature reservoir and the high temperature reservoir. Okay, I'm trying to think how to make this practical. Let's go back to steam engines. They're burning coal, they're making steam. The steam is, water is turning into steam gas, it's turning into a vapor. It's doing work, it's pumping pistons and moving a train. It's condensing back down into water. It's kind of going through a cycle of expansion and contraction, not reversibly necessarily. It's not the ideal situation, but it's that sort of thing. But it's condensing back down around room temperature. It's burning. The coal is creating the steam at some temperature. Is it 100 degrees centigrade or 120, or what temperature is the steam at? You have this differential between where the steam is going to recondense and how hot the steam is that's moving the stuff, and you get the efficiency of the train just off of the two temperatures involved. All right, one of the questions at the end of the book says, What about superheated steam? Would that lead to, I don't know, it doesn't give the answer at the back of the book, but would superheated steam create a steam engine that might be more efficient? Yes, you're upping this temperature right here, so this fraction is going to get smaller, and this is going to get closer to 1. So 1 is 100% efficient. And how could you get this to 1? Well, you would have to get this to what value?
Absolute 0.
Absolute 0. So if you could operate if your cold reservoir was at 0 Kelvin, then you could have a 100% efficient engine, but we can't get anything to 0. So here's the limitation on the whole thing. Nothing can be that efficient. No engine can be 100% efficient. Okay. Where does that put us? Not too far, but let's, here's the homework assignment. Now you're going to need to make some notes at the top because, and Liz, I don't know if you could make these notes for you and Tasha. I didn't put them on there. Let me tell you what, let me write these notes down. Questions, so this is chapter 3 homework. Questions 1 through 4, practice. Okay, I'm not going to grade these, and I really think these relate to chapter 2. All right? So put this at the top of your paper. So, and then I would say start with questions 10, 11, 12, and 13. And that's what we're going to do right now, just a minute. And then do questions 5, 6, 7, 8, and 9. So this is really the homework assignment. All right? 5 through 13. Okay, so let's turn to number 11. Given we just gotten that far.
Can we do the delta H values for each of these steps, or what they would be? It might just be like a. I was trying to.
Yeah.
Delta H has been confusing me a little bit, and I wanna.
Yeah.
We have. I mean, so in there.
Where's my? Yeah, Dominic, I'm not sure I can fill them in right off the top of my head here. But yeah, so there will be some where we have to calculate delta H. And we'll try to come back to that.
Okay.
All right? Take a look at number 11. Number 11 is what number in the book?
This is due Friday.
Yeah, if we're going to have the exam Wednesday, and we're going to try to do like 11 and 12 maybe, or 11, 12, and 13 right now, and get started on 5. So we're going to do a couple of them.
Is 10 kind of a trick question?
See, 10 is... Why? Because it seems so easy?
It seems like you don't need most of the numbers they give you.
Right.
Shouldn't it just be 1 minus Q3 over Q1?
Right.
Okay, that's what I thought, but they just gave you everything else, so I was like...
Okay, see if you get the answer. See if you get the answer that's posted on the next page. Yeah, so it is a trick, whatever you want to call it. There is a lot more information. So number 10. So this would actually flow off of the first definition of efficiency.
Put a period afterwards.
Wait, what, really? It didn't work, Grant.
No. Well, there's some way to set it up. It's 1 plus. So that's what.
Oh yeah, isn't it?
So would you get a positive?
You'd get over 100% if you did that, so you have to do minus. You have to do
Yeah.
plus.
That's for T low and T high.
Minus is only for 2.
Wait, what's happening here?
You don't have a plus, it's plus Q3
Or
over
it's
Q1.
the absolute value. I don't know how they actually define it.
Oh, it is plus. Okay. It is 1 plus Q3. Okay.
You're all getting it.
Sorry.
Okay.
I was going right off of this one, but that one is a plus sign.
And you leave efficiency as a fraction or as a decimal. You don't like not percent. Right.
Yeah, I'd leave it as a decimal. Oh, okay. So here's how the sign shifts. Here, efficiency is 1 plus Q3 over Q1, but Q3 over Q1 is negative T low over T high. So plus that gives you this equation here. And this, what's, Liz, what equation number is that in the book? This one.
You did not give us that value. You said 3.6 is Q3 over Q1 plus Q3 over Q1, but you did not list 1 minus T low over T high.
Okay. Yeah, I'm just looking through here. It is, where is it? It's equation 310. So that one's the equation 310. All right, so those are important equations. And then there are some places where they actually pit those two efficiency equations, use both of them simultaneously to address something. Okay, let's see what 11 is at the thing. Okay, number 11. Yeah, Ryan?
When we're calculating the efficiency using the T low over T high, do our temperatures have to be in Kelvin so that we don't end up doing 0 over anything?
Yep, they have to be in Kelvin. Yeah, and the book, in some cases, will give you a problem in centigrade. You have to figure it out in Kelvin, and then they give you the answer in centigrade. Okay? So, yeah, but it has to be in Kelvin. Those T's are absolute temperatures. Okay, 11 is pretty, 11, you want to go right on into 11?
Yeah.
11 and 12, fall out pretty quickly here. If we want to do all three of these. 13 is further on in the chapter, so we won't do 13 right now. You got 226, is that what that is? 266 or 226? For 10?
Oh yeah, I got 0.267. But
Yep.
So then it would be 0.56 times 4.
Did you do 1 minus 0.44 times 150 plus 270?
No, I did 0.44 minus 4.
That's nice.
Wait, what am I doing here? T low over T high. And T low equals?
Negative 36, degree C.
Can't we
Okay,
get an extra sig fig there?
36.0.
They're like
Yeah, I put
0.1,
36.2.
Yeah.
36.0.
but I got 36.1,
Yeah.
but
Depends on.
but I mean we have that extra
Right.
sig fig, right? Like
Yeah.
it's whatever it is, it's point something.
Well, let's see.
It's not just
Technically, they should have put a decimal point after the 150.
oh I see. Oh yeah, you're right. That makes okay.
Technically.
That is-
So,
yeah.
and on the exam, I mean, we're in such deep waters here. I'm not going to worry too much about significant figures. I mean, if you get, but I don't want you just writing down the number that's appearing on your
Yeah.
calculator.
Think about it.
Yeah, think about it and get me a number that looks reasonable,
Okay.
and we'll be fine. Okay? Because really, these are theoretical concepts, and we want to get into the right neck of the woods, and I'll be pretty happy with that. Okay, let's leave 12 for right now. 12 is pretty straightforward. You got an engine, it gives you the high and the low, tells you what the efficiency is. So, all right, let's go on. Okay, so this was the next slide a little bit. Work done by the gas, expansion, work done by the gas. Compression, work is being done on the system or the gas. Done on the gas. We already said these would be 0. I had a little fun looking up the Stirling engine. Have you done that in engineering class?
I've heard the name.
In some classes, some engineering classes, they challenge the students to go out and make a little Stirling engine. We're not going to look, you can go out and look at 5, 6, 8-minute videos where they've taken a Coke can. They've taken a Coke can and cut the top off of it and got some steel wool, and they make this little Stirling engine. They put a little candle underneath it. There's not even any water in it. It's just got air in it, and it's got a second little chamber and a little flywheel, or not a flywheel, a little crankshaft kind of a thing. And you put a candle underneath this thing, and it's expanding the gas, and cold gas is diffusing back down to the bottom and making it contract again, expand and contract, and expand and contract. And you get this little Stirling engine. So I was embedding the link in here, and my computer warned me not to do it, so I decided not to do it. I don't think that's a hot link right there.
I think it was a virus or something.
Yeah, it said, do you really want to do this? So,
You can just Google it, but
right. Yeah, but it will take 9 minutes to look at it.
oh,
So I'm encouraging you to go, just look up a Stirling engine. It's not a perfect Carnot cycle. It's not doing it irreversibly. It's not doing it real slowly. It's doing it kind of fast, but you can go home and make one of these little motors. Okay, so now just introduce a topic that we won't really settle until chapter 4 is spontaneity, and just start talking about it a little bit. Yeah, book falls off a bookcase, it never falls back up onto the shelf. Waterfall run downhill, sugar will dissolve in a cup of coffee. Gas expands in an evacuated bulb. Iron rusts, but it doesn't unrust. You can ski down a hill, you can't ski up a hill in a spontaneous fashion. Spontaneity. So the second law of thermodynamics, which we're getting to, this entropy, well, the first law, total energy of the universe is constant. Thermodynamics does not tell us. Thermodynamics focuses on energy changes, but not kinetics or how fast something will happen. All right, here now. This seems so obvious, you know, that if you have either a vacuum over here or nothing, air over here, but you have some fragrance over here. When you open that valve, it spontaneously diffuses over to the other side. And I guess we are practically familiar with that. That seems kind of, oh yeah, that's what happens. But why does it happen? If you started out here, you'll never spontaneously see these molecules migrate and congregate all into on one side of the flask. But why does it do that? And this is where Boltzmann made his major contribution in terms of probabilities. He looked at it just in terms of probabilities. Now, imagine that these are these two flasks in the previous thing, and the only thing we have are 4 molecules of a gas. Just 4. So one probable state would be all 4 of them to be on one side. Or all 4 of them to be on the other side. That's probable. That's a probability. Another possible arrangement is 3 of them on one side and 1 on the other side. And if you actually think of these 4 discrete molecules of gas and actually keep track of where they are, you could have 1, 2, and 3 here and 4 over there. You could have 2, 3, and 4 over here and 1 over there, and all those combinations. So a 3 and 1 combination, there are 4 possible ways to get that. But evenly distributed, or 2 on either side, there are 6 different arrangements to get that. So 1, 4, 6. More evenly distributed is more probable. So if you go back to this situation and just think about it, it's the probabilities. If those were all different, and I don't know how many there are. Let's say there's 40 of them, numbered 1 to 40. To get all 40 over here or get all 40 over there, those are 2 possible cases. But to get 1 through 39, 1 through 20 here and 21 through 40 over there, and get 1 through 19 and etc., you end up gets into factorials, number of particles and the number of states that you can develop with them. If you just had 10 molecules of the gas, look, you're up into 3.6 times 10 to the 5th different arrangements. And if you went up to 10,000, look, you're already up into times 10 to the 35,000th possibilities. And if you, excuse me, I felt like I was going to sneeze. If you put Avogadro's number down here, all right, 1 mole of gas atoms, and you look at what are the different arrangements for all of those in those 2 states, you're up to astronomical things. So the even distribution of them is the more probable, is the state. And Boltzmann's contribution is that's what's driving this. That's what's driving this, is that it evenly distributes like that, is got to do with probabilities. and he came up with, so this is what gets into entropy. Probably one other introductory comment here is this efficiency or this, you can end up with a ratio of the heat to temperature ratio, that there is a state function that relates heat to temperature and starts developing this state function, entropy, from it. And we get another state function. So we got internal energy, enthalpy, and now enthalpy, or excuse me, entropy. Another state function. And so Boltzmann came up with this arrangement. So what, 1824, about 30 years later, it's coming up with the entropy equals K times the log of the number of states. That should have been on the top of this state, where W is the number of ways the system can be arranged, the probabilities with regard to the system, and that is an expression of the entropy. Here's Boltzmann's constant, which is actually almost more fundamental than the ideal gas law, although the ideal gas law constant there's a relationship between the ideal gas law constant, Avogadro's number, and Boltzmann's constant. So if you just take 8.314 joules and divide it by Avogadro's number, you get Boltzmann's constant. 1.381 times 10 to the minus 23rd joules per K. Okay, we'll start getting into entropy in how this relates to mixing of gases and chemical reactions, but to try to get our feet on the ground a little bit more with the Carnot cycle, turn to problem number 5. Problem number 5, and it has 3 parts, A, B, and C. It'd be good if I could project that, wouldn't it? Maybe I can. Yeah, start reading problem number 5 and start wrapping your mind around it. Read it and see if you can label some of the numbers that are on there while I'll pull it up here. If you know what I mean. Decide what are those things. Is it initial temperature, final temperature, initial pressure, final pressure? this doesn't want to show up. Okay. All right. Well, we all have it in front of us, so let's try to work off of it. I can't seem to open it up. A Carnot cycle uses 1 mole of an ideal gas as the working substance and operates from a most compressed stage of 1,013 kilopascals and 600 K. Operates from the most compressed stage. The gas expands isothermally and reversibly. So step 1, this is an isothermal expansion. To a pressure, so it goes to a pressure of 101.3 kilopascals. Then it expands adiabatically to 300 K. Right?
That's step 2.
Yeah, that's step 2. And then 3, there's a isothermal compression. And there is a adiabatic compression. And it is telling us, so it's a ideal gas, 1 mole of an ideal gas. It's starting out at 600 K. So the efficiency, this is pretty straightforward.
One max TL over TH. See? I was right, you're wrong.
So what's the efficiency of this process?
0, 0, 0.
Wait, how does the T low, so the two the 2 places that you're measuring. So I guess the 600 and 300.
Yeah, if you go back to the, it comes down and it comes down again. So when you compressed it or expanded it, the second step, at the end of the second step, you're at your T low. And then as you start compressing it back up again, you're going back up to the T high.
Okay.
All right, so that's the efficiency. I don't know we'll work out this whole problem, but Part B asks you to calculate the Q high, the Q low, and the work of the whole cycle. So Q high is Q1. Or the Q at step number 1 would be Q high. And the Q at step 3 equals Q low. Okay, so where do we go with that? If you go back to that original, or the chart we were starting to fill out, at step number 1, what is delta U? 0. So that means that Q1 equals what? Okay, negative work 1. Okay, now where do you go?
You can calculate work, can't you?
Yeah, what equation would you use, or could you use for work?
Negative P delta V? Yeah, or P...
Or delta P.
Something delta.
Uh,
Or is it the one with the
We're
ln?
given moles, so we could use negative nRT, natural log,
Yeah.
BF over BI, right?
You can do it with pressure instead of do P1 over...
Yeah, Ryan's on the right track.
Yeah.
So Ryan, what are you saying?
The work equals negative nRT, natural log, final volume over initial volume. Because we know the moles we have, temperature, R is constant, and we have a final and initial pressure and temperature, which we can use to find volume.
You could just do the pressure form of that equation, right? And do PI over PF. instead
Yeah,
of-
so you got your pressures. Okay? Now, this is equation 2.7. What Ryan had is equation 2.7, and what Liz is on to is actually, this is PI over PF. Oh, log, excuse me. This is the log, PI over PF. This is equation 2.8. Okay, and you can calculate work from there, which again, that's going to equal the negative of that is going to equal Q1. You have to change the sign. You're going to get work 1, but the sign of the Q1 is going to be the opposite of that. But yeah, so these reach back into chapter 2.
Because we don't have the volumes here. They don't give.
Yeah, you
So we-
could probably calculate the volumes, but if you used
Yeah.
equation 2.8, you wouldn't have to. Yes, Ryan?
With that equation, how do we know which work we're solving for? Because we're trying to solve for work 1, but isn't there work 2, 3, and 4 that are also involved in the system? And all the numbers that were given in the question.
Right, they're all works.
Yeah.
What is that, 2.7? That's reversible work. Adiabatic. Well, it's just telling you that the gas expands isothermally and reversibly to a pressure of 101.3 kP. So just in step 1,
That's when you're doing it.
it has gone from 1,013 kilopascals to 101.3 kilopascals
Okay.
in step 1.
Okay. So that's
So you got your initial and final pressures right in that first step. That's a good question. How do you know which work that would be? Okay, so that would give you your Q high. That gives you your Q high. Yeah, you're doing good. Or we're about done here. Let's see, can I give you any other hints here? Okay, now you need Q low. So you got Q1. Any ideas on how to get Q3, Q low?
You could set the two equations equal to each other. you know that 1 plus Q3 over Q1 equals 0.5, you would just substitute Q1 in for your solved value and solve for Q3 that way.
Yeah, do you know what equation you're using there?
3.10, which we did in problem A, and you got the answer 0.5, and then you just set it equal to that.
Are you using this?
No, I was saying that we are giving two equations to solve the same thing. So the efficiency in question A equals 0.5. We can say 0.5 equals 1 plus Q3 over 19.14.
Say that again.
0.5, which is from question A.
Right, that's the efficiency.
Yep, equals 1 plus Q3 over Q1.
Yes, right.
And we know what Q1 is from when we solved it.
Right.
When we solved for Q high, we got what Q1 equals.
Okay, and you can get Q3 from that. Okay, now, I'm going to leave it there. So we got at least two of the works now, but work 2 and work 4, yeah, I'll have to think about the work cycle. So then, how do you get this? We've already gotten that one. And Q3 is going to be equal to negative work 3. Again, because delta U equals 0. So that gives you at least two of the works. But work 2 and work 4 is what we'll have to think about some more. And then it says show that the sum of the Q's over temperature equals 0. So, all right, I'll leave you to kind of dig on into that some more, and we'll pick up and start talking more about entropy on Wednesday. Let me look at my notes, see if there was anything else I wanted to tell you. I think that's about it. Yeah, I think that's it. So exam 1 will be next Wednesday.
Are you going to send out the answers for the past homework assignment before Wednesday?
For what?
For
chapter
chapter 2.
Oh, are the answers not attached to?
No.
They're not?
Some of them are from the book, but there's two problems, the Hess's Law problem and the
Okay.
other one.
I'm sorry, you guys asked some questions about Hess's Law. You want to take 1 minute on it?
Sure.
Yeah.
The sodium, that's the sodium carbonate one?
Mm-hmm.
Yeah.
Let's see, so I don't know, what is that? It's this equation here. Going to what? Sodium carbonate? Is this?
Yes.
Yep.
Plus what?
CO2 plus H2O.
There's a coefficient of 2 in front of the, right there.
And that's it, balanced?
Yep.
Okay, so these three here, you could write equations for the delta H of formation of these. So let's just take that one. 2 sodiums plus a carbon plus 1 1/2 oxygens forms Na2CO3. Okay? Right? And what do you got here? You got a delta H of formation of sodium bicarbonate, whatever that number is. And then over here, you're going to have a carbon plus an oxygen forms a CO2. And you're going to have the delta H of formation of CO2. And then you're going to have an H2O plus oxygen forms water. Let's see, you got to balance that. So 1/2 of those, and you got the delta H of formation of water. Okay?
And you need one more, and it's the formation of NaH. That one, right? Or should
Right,
we do
so-
the formation of that as well.
So you could write this thing
Yeah.
and if you want to, you could write that, 1 sodium, 1/2 of that.
I think you need that to get the right answer,
Yes, you do.
right? You need to
So-
have that in your.
So you're going to have a delta H of formation here for that compound, but write it in reverse
Yeah, and then change the sign.
and change the sign on that energy. Write that in reverse, and you could, there's going to be one of those. And since in this equation there are 2 of these here, you need to do 2 here. So this is going to be 1 hydrogen, 2 carbons, 2 oxygens, and look at what you have here. 1.5, that's, and 1.5, that's 3 oxygens. Okay, so you got a total of 3 oxygens here. Well, if you write this in reverse, 2 of those you're going to cross out with 3 of those, and it'll sum down to just basically that reaction. You follow me? I mean, you can. That's one way of doing it. That's one way, and the other way is just with the delta H of reaction is going to equal the sum of the delta H's of formations of the products minus the delta H of formation of the reactants. You should get the same answer. You get the same answer either way. Yes?
Yeah.
Okay. Okay.
Isn't that kind of doing the same thing though?
Yeah.
Yeah, they're doing the same thing. They're based on the same principles. This would be the Hess's law approach to it, and then this would just be the delta H of reaction equation.
Yeah, that'd be fun. Okay. At like
Yeah,
6 or any time after like 6.